Hello guys, and welcome to my YouTube channel. In this video, we're going to be going over the mechanism for the Robinson annulation. I will be performing this reaction. So the overall objective of the Robinson annulation is to form a new six-membered ring. So if you don't end up with a new six-membered ring, you did not perform the Robinson annulation. In summary, for the general steps of the reaction, breaking it up as per usual. Step 1 is a ketone reacts with a base to form an enolate. Step number 2 is an enolate reacts with an enone. We will be getting to what these things are when we go through the mechanism. Do not worry. I just like to break these steps up for you guys. If you have a notepad out, to write them down and then refer to them as we go through the mechanism to help your brain categorize what we are doing as we work through the mechanism. And then step number 3 is the last step, which is an aldol condensation. All right, so let's say we are given this reaction. And they ask us to propose a mechanism where we have a ketone react with an enone, and we get a new six-membered ring. So starting with step number 1, which is a ketone reacts with a base to form an enolate. So let's find a ketone. Let's choose this ketone. Oh no, why did I not choose this ketone? Well, this structure has an element of symmetry. That means if we chopped it in half, well, the left-hand side is equal to the right-hand side. So the ketones are essentially the same. So it doesn't matter which one I choose. Let's go with the top one. And the ketone is going to react with a base. So the base would be the OET. So let's draw it out. O, and then an ethyl group. So ethyl would be two carbons, carbon number 1, carbon number 2. And this O is going to have a negative charge, and it is a base. Bases like to grab hydrogens. So this hydrogen will be stolen. It will take a lone pair and go 2 in, bada boom. And then the 2 electrons in the CH bond are going to go 2 over. And then the 2 electrons in the pi bond between the carbon and the ketone oxygen we're focusing in on are going to go 2 up. The product of this, if we label the carbons, let's say carbon 1, 2, 3, 4, 5, 6. Nothing happens at carbon 6. Same with carbon 5, same with carbon 4, same with carbon number 3. Carbon number 2, well, there's only going to be a single bond to that oxygen because the 2 electrons in the pi bond went 2 up, so this oxygen will have a negative charge. The 2 electrons between the carbon and the hydrogen went in between carbons 1 and 2, therefore there's going to be a new bond in between carbons 1 and 2. And then the O picked up an H, the green H that it stole. And then the CH3 group on carbon number 1 did not move. So this would be the product of step number 1, which is the ketone reacting with the base to form the enolate, where our enolate is a double bond in between 2 carbons and then a carbon-oxygen bond where the oxygen has a negative charge. That is an enolate. So step number 2 is the enolate reacts with the enone. What happens if they react together? Is this oxygen going to attack that carbon because this carbon is delta plus and the oxygen is delta minus? Nope, we have 2 mistakes here. Let's start with going over why this oxygen is not going to be the nucleophilic atom on compound number 1, and let's say the enone is compound number 2. Forgetting about the enone for a second, let's talk about this structure. And let's say we have some carbon with a bromine, a very simple example. This is a stable intermediate, where stability is inversely proportional to reactivity. So if you increase the stability, you decrease the reactivity. And when a negative charge is on an oxygen atom, it's actually quite stable because oxygen is electronegative, which means that it actually likes having electrons. So if we draw a resonance structure though, 2 down, 2 up, what do we get? Well, there's now a double bond between the oxygen and the carbon, and then carbon number 1, 2, 3, carbon number 3, and this is just arbitrary labeling, would have a negative charge. Is a carbon with a negative charge reactive? Well, yes. You would decrease the stability, therefore increase the reactivity, so increase its ability to act as a nucleophile. So this carbon would attack the delta plus carbon on the other compound, 2 in, 2 out. So this carbon is actually the nucleophile. The same thing happens here. We must consider resonance. So 2 down, 2 up onto carbon number 1. So the reactive form of this compound actually looks like this, where there is a negative charge on carbon number 1. So this is actually going to react with the enone, because carbon with a negative charge is more reactive than oxygen with a negative charge. So now the second thing we have to think about is, okay, well, is this negative charge going to attack this carbon, or is it going to attack this carbon? Once again, the answer always can be inferred by looking at the resonance structure. So let's look at the resonance structure of compound number 2, the enone. If I went 2 over, 2 up, labeling the carbons 1, 2, 3. Once again, this is arbitrary. Well, then I have a new double bond between carbons 2 and 3, and then the oxygen has a negative charge, and then carbon number 1 has a positive charge. So this species is also, you could think, present in the solution, and they're bumping around with each other. What's a stronger interaction? A delta plus minus interaction, or a plus minus interaction? Well, a plus minus interaction. So this negative charge is going to attack that carbon. So in step number 2, the first thing that happened was we put the negative charge on this carbon. Now the second thing that's going to happen is this carbon is going to attack this carbon, and then these 2 electrons are going to go 2 over, and these 2 electrons are going to go 2 up. So now you must count your carbons. 1, 2, 3, 4. So you make sure you do not add or drop any carbons. You can see that this structure pretty much has not changed. So just redraw it exactly how you see it. So you have this 6-membered ring. You have the pink ketone. You have the white ketone. You have a CH3 group. Now you have a bond from the carbon that had the negative charge to carbon number 1. You said carbon number 1 to carbon number 2 to carbon number 3, which has carbon number 4 attached to it, where carbon number 3 has a single bond to an oxygen. That now has 3 sets of lone pairs, so it has a negative charge. And you also have another bond in between carbons 2 and 3. So this would be your structure. So this would be the product of step 2, which is your enolate reacting with the enone. So all that's left to do is perform step 3, which is the aldol condensation, and we also need to somehow form this 6-membered ring. So first, I want to remind you what a byproduct of step number 1 was. We got ethanol. So I'm going to copy and paste ethanol down here. And remember, we have an Na plus floating around as well, so that can be a neutralizer right there. But what's going to happen is, well, we need to get back, because this is in equilibrium with what? It's in equilibrium with the O minus and the Na plus. So that means at any stage in the game, it could lose its hydrogen. Who could steal the hydrogen? Well, a reactive carbon would. So we got the 2 in, 2 onto carbon number 2. Remember, because we always want to attack from the anionic carbon, not the oxygen, because carbon is much more unstable with a negative charge than an oxygen is. So we would attack from here, minus charge on carbon number 2. And then it would go 2 in, attack the H, and then the 2 electrons in the OH bond would go 2 up onto the O. And then the oxygen would have a negative charge again. And then this structure would be neutral. So we must proceed with this intermediate. Remember, what did we just get back? Well, what did we get back? We got an O minus with an ET, so an ethyl group attached. We don't really care about the Na plus in the end. So what do bases do? Well, bases extract hydrogens. What hydrogen could potentially be extracted right now? Well, think we want to form a 6-membered ring. So erasing these labels, and I'm going to erase this hydrogen because it's honestly irrelevant. Let's label these atoms. Atom number 1, 2, 3, 4, 5, 6. Oh, there's 6 atoms. Could that be our 6-membered ring? Yes, if 6 was a nucleophile. So we got to take away a hydrogen on carbon number 6 to make 6 a nucleophile. Who is it going to attack? Well, a delta plus carbon. So the carbon, a part of this ketone. So this O minus is going to go 2 in, 2 up, and we're going to get a negative charge on carbon number 6. So all that happens is 6 becomes negatively charged. And now I'm going to move this guy down here. And now what happens is 6 is going to attack the delta plus carbon 2 in, 2 up. So all I want you to do is draw a 6-membered ring and then draw in the substituents after. First things first, draw the 6-membered ring on the left-hand side that did not move. So the pink carbonyl didn't move. This CH3 group did not move. On carbon number 1 and carbon number 2, which we know are right there, we have a new 6-membered ring. Carbon number 1 is attached to carbon number 6 because carbon number 6 attacked carbon number 1. 6 is attached to 5, 5 is attached to 4, 4 is attached to 3, and then 3 is attached to 2, just like it was in the left-hand side. And then on carbon number 1, we also have an O, but it now has a negative charge. Negative. And then on carbon number 5, what are we missing? Well, we're missing the ketone that was on carbon number 5. There we go. That is the product of the cyclization reaction. Back to this step up here. We also got OH, so we got ethanol. So ethanol is still around, where it can either donate a proton or act as a base. So here, it can get a proton stolen from it, so it can go back to its base form, 2 in, 2 up, in equilibrium with the O minus, and then this whole structure becomes protonated. Now all that's left to do is perform a dehydration reaction, and then that's the product of your aldol condensation. So what's going to happen now is, well, this oxygen could potentially see other hydrogens, H pluses in the solution. So what do we get? Well, we get the equilibrium between this and, well, the OH2 plus, which is the best leaving group ever. So we get the OH2 plus. Oh, that's the best leaving group literally ever. So then this green hydrogen can get stolen by the O minus, 2 in, and we get an elimination reaction. 2 over, 2 out. Peace out, leaving group. And you might ask, why did I steal a hydrogen from carbon number 6? Well, I was told that my double bond needs to end up right here. Therefore, I had to perform an elimination reaction on this carbon. So then finally, what do I get? This did not change. There's a CH3 there. Ketone there on carbon number 5. And then there's a double bond in between 1 and 6. And I have my product of the aldol condensation, and then my product of the whole reaction, which was my Robinson annulation. That was the whole mechanism. All right, guys, I hope this video was helpful. Let me know if you have any questions in the comment box down below, and I hope you had fun with this video. Please make sure to leave a like, comment, save, and or subscribe to my channel if you like my content, and have a great night. Bye!